Hello, everyone. Thanks so much for the organizers to allow me give a poster of my study for this conference. My name is Zixian Wang. You can call me promoter. I'm a second-year PhD student in University of Sydney. Thanks for my supervisors. Today, I will give a brief introduction about my study, which is reliable stellar abundances of individual stars with the MUSE integral field spectrograph. So, as we all know, galactic archaeology is at present being propelled by a number of completed or ongoing large-scale spectroscopic surveys like GALA, Apogee, and LAMOST. These multi-object spectroscopic surveys combined with data-driven models make it possible for us to obtain precise and accurate stellar labels for millions of stars. However, one issue on all these surveys is that traditional multi-object fiber spectrograph cannot do dense fields. In particular, the balls and the clusters, because the fibers cannot be placed too close to each other on the sky, making the observations of clusters and the balls very difficult. Therefore, we need a new instrument which can help to extract the stellar spectra from dense fields. Finally, we find MUSE, which is traditionally used to study galaxies, can be used to overcome this problem. It is a second generation integral field spectrograph that is installed for the VLT of ESO. Since the first light, most of the objects MUSE focused on galaxies, like the left image, mainly helping scientists research on their properties. However, some research groups are using MUSE to observe some dense fields with full of stars. Just to see the red image. Most of them study the radial velocity, temperature log G, metallicity, and some exotic spectra. However, until now, there is not a good way to derive stellar labels of stars in such a dense field. For the MUSE spectra, which is the combination with the combination of DDPen, which is a well-trained narrow network model, we can derive more than 20 stellar labels, which is with the similar properties of LAMOST and MUSE. What if we apply DDPen on MUSE spectra? Well, the answer is yes, for some of the elements. Here, I just showed the flowchart of our method. First, we use temporal MUSE to extract the stellar spectra from MUSE data cubes. And then we use the line spread function to degrade the spectra from 2000 to 1800, which then can can be applied on data-driven pen to derive the stellar labels. And after precision check, we can get our results. To verify our method, we compare the stellar labels using our sample with those from LAMOST samples. You can see the difference is really close to 0 for these parameters, which proves the ability of our method. We also select some dense fields and estimate their stellar labels. Not only we can do this, other surveys, including LAMOST, cannot do that. And we compare the stellar parameters using our sample with those from previous studies, which shows good consistency. Now, this is another comparison using our method, and you can see the trend is really similar as well. Here is my take-home information, and I will stop here. Thank you very much.